So this lecture is on the Huffman coding. It's a compression algorithm that uses the greedy method, greedy algorithm. So I'm trying to compress this message: B, C, C, A, B, B, D, D, A, E, E, C, C, B, D, A, E, D, so D, D, C, C. There are a total of 20 characters. Each one is 8 bits ASCII code. So I have a total of 160 bits. If this is, I have to transmit this. Now, I'm going to look at the frequency of each character. Okay, there are 3 A's. 1, 2, 3. There are 5 B's. 1, 2, 3, 4, 5. There are 6 C's. 1, 2, 3, 4, 5, 6. And there are 2 E's. So I'm going to try and build the Huffman tree. So this is basically known as the Huffman tree, okay, for compression. Now, what I'm going to do is that the ones that appear the most should carry the least amount of bits. The one that appear the least, they can carry more bits. Now, if you look at this here, I'm going to build the tree. There are 5 B's and 6 C's. So if I join these ones, I'm going to have 11 B, C. Now, I can join E and A because they are more or less, the same, frequency. So this would be 5 E, A. Okay. Now, I get 5 here and I get 4 here. I should be able to group those. So this is going to be 9 E, A, D. Okay. So now I have 9 E, A, D, 11 B, C. If I group these together, I end up with 20 E, A, D, B, C. See, that's my root. Now this is the root of the Huffman tree. The way I'm going to do it, how it's done here, each left child here, or if left pointer here is going to be set to 1. The right is 1. The left is 0. The right is 1. The left is 0. The right is 1. Left is 0. Right is 1. According to this, left is 0. Right is 1. So let's see how these characters are represented. So now to represent C, it's going to start from the root 1, 1. So I have two bits. I'm going to represent C, which is, so there's 6 of them. So I'm going to need 1. So it's represented as 1, 1. Now, as for B, it's going to be 1, 0. As for D, which is 4 of them, so 4 D's. As for D, it's going to be 0, 1. See, they're 1 bit. As for A, it's going to be, so there are 3 A's, it's going to be 0, 0, 1. 0, 0, 1. As for E, 0, 0, 0. See, so as you can see, the ones that has the most frequency carry less number of bits. So if I look at this, so A is now represented as 0, 0, 1, okay? B is actually 1, 0. If I put the 0 in front of it, that's not going to change anything. C, okay, so basically this is 0, 0, 1, and B is actually 0, 1, 0, and C is going to be 0, 1, 1, and D is going to be 0, 1. So D is 0, 0, 1. It's actually 2 bits in there. And E is 0, 0, 0. The reason I put them is 3 because I got a 3 bit. And that's basically what we have. Now, let's look at this. 3 bits of E, 3 bits for E, so there are 2 of them, so it's 2 times 3. Plus 3 bits, there are 3 of them, 3 times 3, which is 9. And this is going to be 4 times 2, which is 8. And this is 5 times 2, which is 10. And this is 6 times 2, and that's going to be 6 times 2. So if you look back, I got a 6 here, I got a 9, I got an 8, and 10, and finally 6 times 2 is 12. So if I add these up, I get a total of 45 bits. I got a total here of 45 bits. Now, this is what really gets transmitted. So for me to transmit 45 bits, so I'm going to take a percentage of this. So of 160 bits. So that gives me basically 72% savings. Now, what's going to happen is that we're going to transmit 5 characters and 3 bits each, okay? And then we're going to transmit the 3, and this is how it gets decompressed. So the compression, I'm going to be transmitting 45 bits. So if we transmit the 3, all you have to do is start from the top, 0, 0, 0. If you look at that, that gives me E. So you can represent E in there, and B and C. And this is the good thing about the Huffman tree. It's a compression algorithm. It's very, compact, very elegant, and that's it. So thank you.